So in acids and bases, we had two definitions that we covered. We covered the Arrhenius and the Bronsted-Lowry. The first one in your packet is our sort of our more general, or excuse me, more specific definition, where Arrhenius acids increase hydrogen ions in solution, right? And the bases increase hydroxide ions in solution. So that's really specific. You can always tell sort of looking for the H for an acid and the OH for the base. So like H2SO4, that is an acid, that would be sulfuric acid. MgOH2, magnesium hydroxide, that's a base. NH3, this does not meet this definition. Okay, so we are going to talk about it as an acid or a base here in a little bit, but not according to our this early, very specific definition. However, NaOH, sodium hydroxide, definitely a base. HBr, remember in solution that would be hydrobromic acid. In out of solution we could call it hydrogen bromide or hydrogen monobromide. So that would definitely be an acid. And finally NaCO3, sodium carbonate, doesn't meet either definition either. So these are our X's. All right, so the next definition, the Bronsted-Lowry definition, is a lot less specific. It's really basically talking only about the hydrogen ions. So acids release hydrogen ions, or remember, those are just protons. And the Bronsted-Lowrys accept hydrogen ions or protons. So notice there's no mention of the hydroxide ion here. We're really looking just as sort of this transfer of a proton. You could actually think about Bronsted bases as pulling hydrogens off of other things. So now we've got a lot more leeway in what can be acting as an acid and a base. Okay, so a couple more terms that you need to be aware of. Let's make sure I'm all up here. So monoprotic, diprotic, triprotic just have to do with how many hydrogens they can release. So let's do hydrogen and bromine. Hydrobromic acid, that would be mono. Mono means one. Diprotic, any of our sulfurics, hydrosulfuric, sulfuric, sulfurous, they're all diprotic. Triprotic, remember the phosphate ion is a -3, so anything with our phosphate ions like that, the phosphoric acid would be a triprotic. Okay, so a couple more definitions for us in here are listed below. And let's see if you have troubles with any of these. They are in unit, unit 8, I think is when we did acids and bases. Let's just trying to remember. So the amphoretic, this just means something can act like an acid or a base. Water is an example. Let's see, neutralization. That happens when we combine an acid plus a base and we bring the combined pH back down to neutral or down towards 7, and we end up with a salt and a water. Dissociation is when we break apart the ions. We are not decomposing, but we're just temporarily breaking apart ions. Decomposition would take these elements and decompose them into neutral molecules or atoms. A dissociation just breaks them down into their charged ions. So for example, calcium carbonate in decomposition would split into, let's see, we would end up with a little bit of CO2 and a calcium oxide. Oops, don't need that, like that. But in dissociation, we just end up with a positively charged calcium ion and a negatively charged carbonate ion. So with the NaOH decomposition, we should end up with a sodium and a water. That's not balanced, obviously. Actually, I think we end up with a sodium oxide and a water. And then for the dissociation, just the sodium ion and the hydroxide ion. And I'll leave the other two for you to do. Just remember, dissociation, we always have these guys are charged. Decomposition, they're neutral.